Thank you, Christos. Good morning, everyone. Thank you for inviting me to Georgia Tech. My first interaction with the School of Aerospace Engineering at Georgia Tech was the first department that offered me a graduate fellowship when I was applying to come to the US more than 40 years ago. So I'm enormously grateful. Even though I didn't end up here, I've had a lot of interactions with Georgia Tech over the years. So it's nice to be back. The work that I'm going to present here today is pretty much all of it was done in the last about 5 to 6 years. And I've been very privileged to have the opportunity to collaborate with a large number of very talented people whose names you will see in the various slides. And the motivation for this work is try to see if we can combine within the core of material science and mechanics of materials. There are so many other areas that have implications for new understanding, and also to develop new engineering products and processes, whether there is an opportunity to go way beyond what traditional knowledge of biology, traditional knowledge of nature, or more recently, computing power, whether it's through computational simulations or even AI alone can provide. So that's the goal of this. Because it's the aerospace department, I thought I should start with this picture. We know that nature for millennia has provided inspiration. None of this is new. The V formation flight of birds, that's how fighter aircraft fly. And here it's driven by aerodynamics. In the case of animals, small animals, nanoscale properties of gecko, for example, their feet, are inspiration for developing synthetic ways of enhancing adhesion on surfaces that would not adhere. And many people, hundreds of people have published on these kinds of things. But there are also interesting phenomena in nature that nature does things in a certain way. For example, when you want to make hinges in engineering structures and devices, nature doesn't make hinges the way engineers do. It does it very differently through structural gradation, microstructure gradation, and adaptive responses to things like humidity, light, and heat, rather than the way we do it in engineering structures. So despite all the progress that has been made, there is still a lot more to learn with respect to how nature works. Add that to, in the last 5 years, the significant advances in computing and also in AI and machine learning and artificial intelligence. So the overarching theme of our current work is the following. We can learn a lot from nature, and deep learning from nature beyond biomimetics, taking what nature does, copying it for engineering. We can bring in digital tools to interpret how nature does, and digital tools to enhance what nature does, so we can do things that doesn't happen either in the natural world or through current engineering, and it can be better than both. So the outcome is much greater than the sum of the parts. Add to that machine intelligence with large language models, ChatGPT, AI, etc. We can significantly improve our understanding compared to without them. If we can do that, how do we use both of those to augment human intelligence? So this is field non-specific, but our goals are the following. So human intelligence to be augmented by deep learning from nature and machines. By nature, we mean plants, birds, and animals. We want to demonstrate new scientific, so this is another important goal of this. Can we demonstrate new scientific understanding with a combination of these, combination of at least 2 or more of the 3 here, that cannot be achieved without AI? What can we do with AI that cannot be achieved without AI? Can we show examples of this? The third would be, can we take materials and dramatically change their properties by understanding nature better and also bringing computational tools and AI in ways in which we have not done before? That's the third. Of course, in all of this, coming as an experimentalist, we don't want to hallucinate. We don't want to have the AI program to hallucinate. So we will not trust anything until we can show that experimentally. And it has to be in compliance with facts, evidence, experimental validation, and of course, physical laws and laws of thermodynamics. So that's the overall goal. And the idea would be to go beyond classical or traditional biomimetics and beyond classical computational modeling and simulations. So the outline of this talk, I want to go into some depth. So I'm going to avoid discussing things like what process we used, what chemicals we used, what experimental methods, etc. They are in the publications that are cited below. But to go into some significant depth on the concepts, I'm going to focus on 3 areas. First, I'm going to start with plant science, take materials from nature, and then use that with digital tools for engineering purposes. Second, I'm going to take a material from nature, which is the most difficult to deal with, and see how we can use AI to understand the material better and use that to design new properties of the material. And last is the intersection of biology, especially human health, and these tools, nature and machines. How do we interpret them? So in each of these, I'll go through 1 or 2 specific examples in detail. So first, on the first topic, on plant science, plants use tissues, architectures, in very interesting ways to develop shape, and they use environmental stimuli to change the shape in ways in which it is not obvious. So here is a particular example of a pelargonium plant species, and on the left, you see the wet state of the plant, of the awn of this plant. On the right-hand side, you see the dry state. Just by changing moisture, rain versus sunshine, can change the shape of this plant quite dramatically. And this was the inspiration behind our first work, which I'll go through in a little bit of detail shortly. So what this plant is able to do is, but just by being responsive to hygromorphic shape changes, it can coil in interesting ways, it can develop shapes, and as a result, it can adapt to natural environments in very significant ways. So this was the inspiration between the work that we started in 2019, and my main collaborator here is Professor Namjoon Cho, who is a professor of material science at NTU in Singapore, and we had several joint students and postdocs. And the idea behind this is the following. So we all know, especially in the springtime, pollen is a very interesting material that causes allergies. So plant pollen, in here we have a sunflower pollen as an example. Plant pollen has, the microstructure of pollen is shown in the middle figure on your top left. It has a hard exine, and then it has an intine. And the microstructure of the pollen, and pollen is considered the diamond of the plant kingdom. It's very hard. And pollen is allergenic. So one of the questions we had in our first piece of work was whether we can take pollen that's available in abundance in nature, and I didn't know this until 5 years ago. I found out that you can actually buy pollen on Amazon for a song, Amazon, JD.com, you name it. You can buy kilograms and tons of it for relatively inexpensive price. I didn't even know people were in the business of collecting it and selling it in large quantities. How can you make money out of it when it's so cheap? So here is an example in your bottom left, a jar of pollen grains. So what we did was, with Professor Cho and his coworkers and our collaborators, is to use a process that's very similar to soap making. So you control the temperature and time and the concentration of potassium hydroxide, and you go through a chemical process that's very similar to soap making. You convert the hard allergenic pollen grain into a non-allergenic soft microgel. So the microgel is of the order of a few microns, few tenths of microns. It depends on the plant species. In this case, we focus on sunflower plant. So you create a microgel. The microgel is like a grain in a metallic material. It becomes a building block, and it's completely non-allergenic. So can you now take the microgel and make materials out of it? And it's completely plant-based. So can you use the properties that plants use naturally to create products that with the microgel, just like you design materials with metals or ceramics or plastics, can you do with plants? And that's the goal. So that's essentially the principle behind this. Now, if you look at the bottom right of the schematic that you see, we start with the pollen grains. Then we go through the soap making like process, create a pollen microgel. Then we use a suspension technique, and all of that is described in the papers that are cited here. Just for curiosity, we decided to make the first simple product. And the product is a piece of paper, 8.5 by 11 paper. Paper is usually made out of wood. So you chop wood, chop the trees. You go through an elaborate chemical process that is highly energy consuming. It also involves transportation of wood, and you create paper. So we thought, why don't we create paper out of pollen, and how good this paper will be. So we created an 8.5 by 11, or any size you can create, paper out of pollen. That's what comes out. The next question is the paper any good? So we can print it in an inkjet printer or a laser printer, regular laser printer, etc. Fine. So first we can make a product out of it. But this is made out of pollen. But we also know that pollen plants in general, many of them, are hygromorphic. They can absorb water. They react to water. So can the pollen paper have specific properties that make it unique, so that can you have a self-propelling robot? Can you digitally create a shape? This is where the digital technologies, digital tools, and natural materials comes in. So can we create a digital tool out of this? And then, can we create a shape? Can you sit in front of a computer and design a shape, a very complex shape, like an orchid flower, which has many different nuances to this? And what else can you do with it? Can you make flexible electronic substrates and things like this? So anyway, that's our next goal. So we decided that we will use principles of engineering with pollen paper to create essentially self-morphing structures that we can design in front of a computer digitally. So what you see here is on the left, the yellowish strip is a pollen paper. Then we take that paper, we feed it into an inkjet or a laser jet printer, and we can print ink on it. So now think of this as a thin film on a substrate. So you have two materials. The pollen paper is hygromorphic. It reacts to water and moisture. So if you put paper in the room in your hand, and the humidity of the room either goes up or goes down, if the humidity goes up, the paper absorbs water, it swells. If the humidity goes down, it releases water. So in either case, change in humidity causes a change in volume of the paper. But the toner, the ink, doesn't respond to moisture. So you have a bilayer material where one layer changes geometry in response to, instead of temperature, we have moisture here. The other layer doesn't change. So if that is the case, then the two-layer system has to curve and change shape. And you can decide how it changes shape by printing shapes on it. So we decide to print lines on it. So when you print lines on it, on a piece of paper that is sensitive to water, what you find is there are different variables. The angle of the line with respect to the orientation of the paper, the spacing of the line, and then, so those are two things. Theta is the angle with respect to a reference coordinate, and then you have the pitch if it curls. So now let's see what happens. So you have, on the right-hand side, you have 0 degrees, 30 degrees, 60 degrees, and 90 degrees. Now, as engineers, we can go to town with it. We can take plant material, and we can do a number of things with it. So the first thing I want to show you is a video of what happens when you take the strip of paper, pollen paper, which has lines patterned on it. We're going to start with 0 degrees, go to 30, 60, and 90 degrees. We change the moisture. We go from high humidity to low humidity back to high humidity. See what happens. So here is the actual experiment speeded up. At 30 degrees, you can see the shape change. At 60 degrees, you have a different shape change. At 90 degrees, it starts to coil. So all we did, the only change is the orientation angle of the lines on the pollen paper. So now, having demonstrated this, we can do a finite element analysis because it's a simple expansion problem of 2 layers. We know the orientation. So we do a finite element simulation from 0, 15, 30, 45, 60, 75, and 90 orientation for this paper. Experimentally, on the left, this is what you find, and finite element simulations will give you the prediction. You can predict it quite well. That means now you can design different shapes and different geometries of a very eco-friendly material, which is non-allergenic. So one of the toughest things to create digitally is the orchid, which is the national flower of Singapore. So we decided to create an orchid. So how do you create an orchid, and how do you create folds and curls? So on the top you have 2 different patterns that are joined together, and you can actually, in a single strip, you can print 2 different patterns and different orientations. So if you change the humidity from high humidity to low humidity, say 30, 40% humidity to 75% humidity, it'll curl differently, and it's shown here. In the middle, you have the same strip at different angles, and you see how that curls. Note that there are no hinges here. So you can create a hinge without having a sharp corner, a nail, a groove. That's how nature does things. And you can show that simply with paper here. And you can see on the right-hand side, 4 or 5 different patterns and how the geometry takes shape. In the bottom middle, you can actually see initial stages of evolution of an orchid as designed by a first-year student sitting in front of a computer and just changing humidity in the lab. So now we can get a little bit more ambitious. So if we can make a piece of paper, can you make a box? So you want to put something in a box. The box folds itself just by changing humidity. Once it folds itself, you coat it with something so that it's no longer sensitive to humidity, and then you ship it, and then you can open the box, and you can reuse the box over and over again. And can we demonstrate that? Can something as simple as a piece of paper fold itself into a box? If so, how does it create the corners? How do you create the corner? Because nature doesn't use hinges the way we do as engineers. So here is the next video. You can see the hinges are just stripes that are printed onto the paper. And we put a very heavy metallic piece in the middle so that the box will fold itself just by changing humidity. Now, if you go back to high humidity, it opens up. So you can open and close it And you can freeze the shape if you want. So at the bottom right, you see there are coatings, natural coatings that you can use, chitosan, petroleum jelly, and many other things. You can freeze so that it doesn't become hygromorphic anymore. So the next question is, can you print something in it that can survive for a long period of time? So here is an example. So because it's sunflower pollen, we decided to print Van Gogh's sunflower picture in color. And here is the video of that. So we dip it in deionized water. And you can see the printing is very good. You can make the paper completely white if you wish by treating it with certain agents. So this is what happens. Then the question is, can you unprint it? Both for cybersecurity, you can shred the paper, or whatever you print, you can unprint and reuse the paper without losing the mechanical integrity of the paper. Can you do that? The answer is yes. So here is one way to do this. So how do you unprint? So we start here with the paper that was just printed with the Van Gogh sunflowers. We use a solution. We completely take everything out. This is printed using a regular printer, regular inkjet printer. Then you put it in ethanol. You get your paper back. Now you use the same paper to dry it, you reprint it. Keep doing it over and over again. So we did that 9 times. The student who was very good, who was working on this, decided 9 times was enough. It was getting to be boring. So here is the repeated picture. So we started clock 0 time. We go clockwise. So first you see the Van Gogh printed, unprinted, plain paper, recaptured, reprinted with Mona Lisa, unprinted, printed again with sunflowers. The same process repeats multiple times. You can print and unprint with this. So this is my last slide on this. If you compare the wood paper making process from wood versus paper making process with pollen, in the top, this is all the current steps that are used to make paper out of wood in industrial practice. Of course, the bottom process right now is only in the lab, done by students. It's not commercial scale. But the steps that are necessary, even at industrial scale-up, are relatively small. So it's much smaller. As a result of this, you have potentially substantially lower cost in doing this. So that's one advantage of doing this. We didn't intentionally make a cost estimate of this because you're comparing apples and oranges, a commercial scale versus a lab scale. But this is the step that's involved. On your left-hand side is the commercially available pollen grains that can be your starting point. And here are examples of pieces of paper that you can make. You can also make other things. You can make cardboard boxes. We've only been able to make so far at the university level about 100 micron, 200 micron thick objects. In principle, you could make much thicker objects on a commercial scale. That has not been done yet. You can also make substrates for flexible electronics. So on your left-hand side is a heating patch, and it shows the temperature. Then you have, if you go for electrocardiogram, they stick plastics to your chest to do the measurements. Instead of that, this is pollen substrate, which is biodegradable. And on the right-hand side, you have the electrocardiogram from plastics versus pollen substrate. It's essentially the same result. The last thing I want to show to end this portion of the talk is another example of a very different. We've looked at 7 or 8 different things. I just showed you pollen. This is another plant. This paper was just published this week called Rapsis excelsa. This is in collaboration with another group at NTU as well, the group of Professor Jimmy Shah. And so here, this particular plant, on your top left, when it's raining, the plant is completely opened up. When it's very dry, it closes up and folds. It folds without hinges. And you can control the folding, and it has something called hinge cells in the structure of the plant that enable it to fold. So we thought we'll do a fun project as a student project. Can we take this plant, and we made a lot of measurements. We used modeling to predict the correlation between hydration and shape evolution and folding. Then we created a synthetic structure based on this. Here what you see is a bilayer, just like in the previous example I showed. Here the two layers are an elastomer and a hydrogel. And the hydrogel is responsive to moisture. And so the question was this: let's say you are sitting outdoors in a cafeteria and you have an umbrella at your table and the sun is shining bright, the umbrella is folded. Suddenly it starts to rain. So the umbrella automatically senses moisture and it opens up, just like the plant would. So just mimicking nature. So here is the demonstration that you can actually do this. So you can go from your right to your left. So you go from a dry state when it's folded, so figure 3, to the left when it's completely open, just by changing moisture. And you can go back and forth. You can open and close. And this is a synthetic version of what nature does. Again, here there are no hinges to do this. And it's essentially mimicking nature in interesting ways. So let's park that for a minute, then go to the second topic. Again, sticking with nature. The hardest material found in nature is diamond. And diamond is very interesting. Nature has a way of making it that's pretty remarkable. It's not only the highest strength material, it's not only the hardest material, and if you make it pure enough, it approaches, you can achieve theoretical density in the lab in deforming diamond. That theoretical density is the highest of any material you can achieve, which is pretty remarkable. So that's lesson 1 from nature. The second lesson is, since the launch of the National Nanotechnology Initiative in 1999, there's been a lot of work done on effective size scales, going from macro to micro to nano. And one of the lessons we learned from a large number of materials is that at the nano scale, materials behave very differently than even the micro scale. So if you go from a millimeter size specimen to a micrometer size specimen to a specimen that's tens of nanometers, when you go to the nano scale, the surface to volume ratio is very high, the defect density is very low, so the properties, including mechanical properties, are completely different. That means size scale matters. So we decided that we thought, why don't we take nature-made material diamond, and go to the nano scale, and we know how diamond works at the macro scale. So if you buy a little piece of diamond and you try to deform it, it's very brittle and elastic, linear elastic, until a strain of about 0.1 to 0.2%. And then it fails catastrophically in brittle fracture. And it has no plasticity, no nonlinear elasticity, no large-scale elasticity. And that we know very well. If you go to the micro scale, the same thing will happen. So we decided to check if that's true in the nanoscale for the hardest material in nature. Of course, we didn't want to buy diamond and do the experiment in the lab. It can get pretty, without knowing what the outcome was going to be. And we have to, especially if you're a previous director of NSF, you want to make sure that you spend taxpayer money very wisely. So we decided to do synthetic diamond. So this is how we did this. One of my former postdocs, Professor Yang Lu, who's on the faculty of a university in Hong Kong, he and in his lab, they made a silicon substrate with a continuous diamond film, and then you etch the diamond into nano needles. So you have silicon substrate, and diamond nano needles are sticking out of the surface. The length of the needles is a few hundred nanometers, and the diameter changes, but it's of the order of 100 to 200 or so nanometers diameter. So you have diamond needles on a silicon substrate. It's a CVD-made synthetic diamond. Okay? And so we want to deform. So our hypothesis was the following. Because nano behaves very differently from micro and macro, if you have a micro needle or a macro needle of diamond on a substrate, and you were to come and try to bend it, it won't bend. It'll have a linear elastic deformation, then it'll have catastrophic fracture, or what is called cleavage fracture. But in the nanoscale, we suspected that it has to have some form of nonlinear elasticity. So can we do this? The only way to find out is to do the experiment. So we took this substrate with a needle, put it inside an atomic force microscope. We came with a diamond tip in the microscope. We have a diamond needle, a diamond tip pushing on the diamond, try to bend it. You bend it a little bit, see if it bends. If it bends, you videotape it, and then you retract the diamond, see if it goes back. Keep doing it over and over again with increasing deformation, and see will it eventually break. So when we did the experiment, the next picture is going to show a video. So this work was done in collaboration with a group at MIT, a group in Hong Kong, my former postdoc group in Hong Kong, and our group with Professor Ming Dao and a couple of postdocs at MIT. And what we found, to our surprise, was you can actually bend the diamond just like you bend a piece of metal, like aluminum or copper. So the video that you're going to see shows you how the experimental bending takes place in situ in the microscope at high resolution of the nano needle. It also shows on the side a finite element simulation of exactly the same geometry for nonlinear elastic deformation of the diamond needle. Diamond can be single crystal or polycrystal, and we did both. The first video that you're going to see is single crystal diamond, and the simulation is for exactly the properties of single crystal diamond for the same crystal orientation. So you can see on the left, the diamond indenter comes and pushes, and then when it retracts, the needle turns back. Needle goes back. On the right-hand side, it's a finite element simulation, and what is the color contours are on the tensile side of the bent specimen. You have the maximum tensile strain, and what you find is that the maximum tensile strain is as high as 9% before it breaks. 9% strain in diamond at room temperature, and pretty much ambient conditions, but in vacuum, in a vacuum environment. We had to be very careful with friction. So could friction play a role? Because diamond to diamond friction. So in the finite element simulations, we put in friction coefficient of 0.1 or friction coefficient of 1. It turns out it makes no difference. And also we know the stress strain curves, or force displacement curves, they show very little hysteresis, which is an indication of friction. So having done this, now this is polycrystalline diamond, and you can see catastrophic fracture at about 4% strain. So single crystals, we can push them to 9% strain, and polycrystal diamond, you can strain them to up to 3 to 4%, which is pretty surprising. So we summarized all of this in this picture. So what is plotted here is the maximum elastic tensile strain until failure. And you have F denotes the friction coefficient. So it's either 0.1 or 1.0. You have single crystal, when it fractures, When you have just elasticity, it means we went all the way and came back, and it did not fracture, but that was the maximum strain we were able to obtain. So we did multiple specimens, multiple videos. So the point of the story here is that you can get a strain as high as 8 to 9% maximum in tension in diamond at room temperature at the nanoscale. And the reason behind this is you have very few defects. It's very clean, even though it's a CVD-made diamond. So we have, in the published paper in Science, we have a lot of transmission electron microscopy images of the specimen itself, and also atomic resolution micrographs. If you compare that to the polycrystal has many grains, it has many defects, so that you would expect it to have a lower ductility or strain to failure, and it fails around 3 to 4%. On the left, you see the bulk diamond. Bulk diamond almost has no plasticity or inelasticity, which is known. So we published this in 2018. A group in China, in Zhejiang University, they decided to test our results out. So instead of synthetic diamond, they actually took natural diamond. So they bought diamond. They knew the crystallographic orientation. They used focused ion beam to cut the diamond into nano pillars. And then they had different crystallographic orientations. So 100, 111, 110, etc. They pretty much repeated our experiments, and they did some other very clever things, and they showed exactly what we found. And they showed that the fracture strain they got was 9.4% in their natural diamond experiments. And in certain orientations, they were able to go as high as 13%. So the results were independently confirmed in natural diamond in a very different group. So here are the images from their experiments, which was published in 2019. So the next question is, we can bend diamond, so what? So what do we do with it? Diamond, it turns out, is also not only a mechanical, it's used for cutting tools, it's used as indenter, it's used in many mechanical applications, but it's also one of the best electronic materials. Unfortunately, it's not very useful because you can't fabricate diamond that easily like silicon. So here is a picture from Fujita, which summarizes electronic properties of various materials used for microelectronic chips and in optoelectronic applications for different colors. So this is the electronic band gap of different materials as a function of bond length. And here's the wavelength of light and different colors that you get in the spectrum of light. And what you see here is silicon is here. Silicon has a band gap of about 1.2 electron volts. And it's the most user-friendly semiconductor material that's widely used. Diamond has a band gap. It's an ultra-wide band gap material, and it has a band gap of 5.6 electron volts. Now, we know from prior work in the chip industry, Intel and IBM commercialized it 30 years ago, in silicon, if you can put a small amount of strain in silicon, you can improve the clock speed of your computer chips by a factor of 2. A 1% strain can improve the clock speed by 100%. If that is the case, we asked ourselves a lot of holy grail questions. If diamond has a band gap of 5.6 electron volts, without changing the composition, without chemistry, just by mechanical means, can you change the band gap of diamond from 5.6 to something much lower, say very close to compound semiconductors in this range? So can you do that? If so, what kind of strains does it take? Can you do that with the kinds of strains that we have already demonstrated for nanoscale diamond, which is up to 9%, 10% or so? The other question is, can you do that without causing any phase change so that diamond doesn't become graphene or graphite? So graphitization of diamond. So carbon, the form of diamond is preserved, and you do this transformation. So can we do this? So that was the main question we were after. The motivation behind this was something that started in the 1980s from Bell Labs, and Intel manufactured so-called strained silicon. This is a picture from IBM, and what you see here is a strained silicon channel, and you can see the scale here. This is 50 nanometers. In the computer chips that were being made starting in the 90s, this strained silicon channel with only 1% strain could result in a significantly high improvement in clock speed and performance. So if you can do that with 1%, can you do that with 5%? What would 5% yield? Can you improve the properties? But it's very difficult to demonstrate that in an experiment. So first of all, can you change the band gap? And how do you change it? So to go back to this, so how do you even go about proving that the band gap can be changed? So we've shown experimentally that we can bend diamond in the nanoscale. That's not an easy experiment to do. So we've demonstrated that. We showed that you can get a strain of 9% in tension, maybe 13% in compression. That is demonstrated. We can do finite element simulations and show that when it fails at 9%, that's very close to theoretical strength of diamond. That we have demonstrated. But how do we demonstrate band gap, especially when it's localized and it's highly graded it's not uniform. So we decided to do density functional theory calculations. So we did 1,000 calculations in regular computer power, which you can do over a period of a few days with the computer facility that we had with my. So this part is done in collaboration with Professor Ju Lee at MIT, who has been my long-term collaborator. And so we could do 1,000 density functional theory calculations. So if we do that, can we use machine learning to take the density functional theory calculations? Can we use the calculations that we have from finite element simulations? Can we use our experimental data and go in 6-dimensional strain space? You have 3 normal strains, 3 shear strains. In 6-dimensional strain space, can you identify a particular combination of strain that will lead to a band gap of 2.5% or 3% for diamond? If so, what is the strain? Even better, can you identify a strain that will make diamond completely metallic so that the band gap is 0? So diamond becomes an electrical conductor. Can we identify it? There is no way we can do it computationally today. There is no way we can do it experimentally. So now comes machine learning. So we use this program. Again, I could spend an entire hour on the machine learning algorithm, so that's in the publications. But to say that this is an example where without machine learning, we could not do what we were able to do with machine learning. So here is the outcome. So this is the experiment we did. This is the compressive strain of the bent diamond nanoneedle. This is the actual experiment. This is our experimental specimen in the microscope. This is a computational simulation of the compressive strain here. We can go from 0 here, no compressive strain is here on the bent specimen. There is 0 compression here, and it goes from minus 10.8 to 0. This is the tensile strain. So on this side, you have the tensile strain, and the tensile strain is as high as 9.6%, and you have compression here. If you do the same figure with band gap, both on the tension and the compression side, because band gap changes from both tension and compression, this is what you get. For the same amount of deformation of the bent diamond nanoneedle, you can get a strain that approaches, if not quite 0, it approaches 0 on either side. And using other calculations, so we use strain energy density, which is strain energy per unit volume, under compressive strain, and we calculate the band gap. In compression, we can go to safe metallization without phonon instability in the case of diamond. In tension, you have to be careful. You could trigger phonon instability if you go beyond this particular strain. But there you can get about 1.2 electron volts, which is very close to silicon. So this has been demonstrated computationally with machine learning. Without machine learning, we couldn't do this. Then we created out of this a 6-dimensional space of principal strains, epsilon 11, epsilon 22, and epsilon 33. It essentially tells you the entire map of strains where you can make diamond behave like a metal. So you have direct band gap, you have indirect band gap, and you have the boundary where you get phonon instability, where you get the structure changes from diamond structure to a graphitization structure. So, and then if you take a slice, a 2D slice at a particular strain, this is a 2-dimensional representation at that particular plane of what the properties are going to be like. So you have direct band gap, indirect band gap, and then I don't want to go into the details of this. You can also look at the energy space, and you can look at the energy spectra and so forth to show where the band gap occurs and how. In addition to changing the band gap, diamond also has very interesting thermal conductivity properties. So lattice thermal conductivity of diamond, just from the bending experiment, can be changed from 800 to 3000 watts per meter, Kelvin, the units that we use here for thermal conductivity. So in some cases, for very high strains, you can actually change it by 2 orders of magnitude, both in tension and compression. So this sort of gives us an example of a situation where you can take the hardest material found in nature, bring in experiments, bring in high-resolution microscopy, take the lessons we learn at the nanoscale, then bring in machine learning algorithms to identify properties and performance metrics that would not be obvious without the machine learning algorithms. The remaining next 5 minutes or so, I'll conclude with the last example of learning from, I'm just going to show one example here. Can we use machines? Now we have 2 types of machines. If you're an experimentalist working with biomedicine, you can create a microfluidic device that is your experimental machine. You have your artificial intelligence engine, which is your machine learning algorithm. Can you combine the 2 and bring in patient data, patient information to do something that cannot be done without this artificial intelligence? So we used for this a particular example of diabetes. So diabetic retinopathy is a consequence of diabetes. So in this particular experiment, so this is a picture taken from a patient's eye, and this is published in the literature in 2018. This is our experiment. One of the consequences of diabetic retinopathy is that in the small blood vessels in the eye, the patients begin to get little bulges or sacs that go off of the blood vessels, and these grow in size and grow in number as the disease progresses. So what you see here is blood sample from a diabetic patient that is run through a microfluidic device that has different sizes of these bulges so that we can quantify the velocity fields, the pressure fields, and get the full set of fields from the microfluidic experiment, and we can take videos of this. Add to that the 2D image of the picture of the eye from the patient, from the clinician, and then you combine the 2, and then bring in your machine learning algorithms, and then you allow for physics-informed neural networks. So essentially, you want to make sure that the fluid mechanics of this is in compliance with the various partial differential equations that we expect it to follow. So if it's solid mechanics, we have equations of equilibrium, we have equations of compatibility. In classical fluids problems, how do you comply with physical laws? You ensure that physical laws are followed. This work is in collaboration with, the machine learning part is in collaboration with Professor George Karniadakis at Brown University and his research group, and my collaborator, Ming Dao. So you provide penalties for data mismatch, boundary mismatch, and physics mismatch between the machine learning predictions and the experiments, and keep doing it until you get the right convergence. So here is an example of the fields that you can create: velocity fields, pressure fields, and shear stress. And the advantage of doing this in practice is that you can enforce no slip boundary conditions. You can back out pressure, shear stress fields, and in fact, it provides significant advantages over traditional particle image velocimetry. And as a result of that, you can directly connect with disease monitoring for the particular patient. So it's still some distance to go, but it points to the opportunities that machine learning can bring in this particular example of diabetic retinopathy. My last slide is an example of different types of hereditary blood disorders and how computational tools, this is without machine learning, but we can add machine learning to this. So what you see here in our spleen, the toughest mechanical fitness test in the human body is the interendothelial slit, which is shown here in this figure right here. This slit has 4 microns by 1.2 microns, and this is what the blood cell has to squeeze through. An 8 micrometer diameter human red blood cell has to squeeze through this. So what we show here is doing the entire molecular spectrum network of the red blood cell and simulating it and squeezing it through this through a technique called dissipative particle dynamics. When it squeezes through this, you can actually, I'll show the video in a second, how a red blood cell behaves. For clarity, we show only half of the red blood cell. So if you click on this image, you can see how the healthy red blood cell squeezes through this. If the patient happens to have sickle cell disease, the cell becomes sickled in the deoxygenated state, and it cannot squeeze through the interendothelial slit, and you can see what happens. It gets stuck. And splenomegaly, or the enlargement of the spleen, is one of the consequences of severe cases of sickle cell disease, which unfortunately primarily affects people with inherited sickle cell trait, primarily people of African origin. Spherocytosis is a disease which is very similar to sickle cell disease, but from a very different origin by vesiculation. And where the little membranes bead off, it affects people of Scandinavian origin. Roughly 1 in 5,000 people is genetically, in Scandinavia, is genetically predisposed to spherocytosis, where the blood cell is not a disc, it's a sphere, and a sphere cannot squeeze through a small tube of smaller diameter. So you can see here how the vesiculation is simulated by the models. And in fact, there are thousands of pictures in the clinical database which show these vesiculation phenomena, and you can pick it up through these simulations. And the last one is elliptocytosis. It's an unusual shape of the blood cell which affects some people of Asian origin. And you can see how lysis takes place in elliptocytosis, and there is a lot of clinical evidence and pictures of this. So the point I'm trying to make is by bringing machines into what nature does, we can actually elucidate the mechanisms in new and interesting ways. Now you add, in this particular case, machine learning to this, it can significantly enhance the outcome. So with this, I want to close with this video of about 50,000 starlings doing a dance at sunset. And this has nothing to do with aerodynamics. Unlike the V formation pattern, which is aerodynamics driven, this has nothing to do with aerodynamics. In fact, the theory is that they want to cluster one another for body heat and also to protect from praise. And it's amazing how, and this is still not understood. So there is a lot we have to learn from this. So I want to summarize. Hopefully I've convinced you that nature intelligence and machine intelligence together can lead to new scientific discoveries that cannot otherwise be obtained that easily. Nanostructured and nanoscale features in nature display many mechanisms. There are potential pathways to new science and new design of properties. And the last thing I did not get into in detail in the talk, but it's in the published work that I cited here, multi-fidelity approaches, low fidelity and high fidelity machine learning approaches together enhance our understanding and predictive capabilities for greater accuracy. So both in engineering design and in disease monitoring. Thank you. No, this is Washington, Cherry Blossom, Jefferson Memorial.
Thank you so much, Subra. Questions? Yeah, please go ahead.
I have a question regarding, can carbon paper completely replace wood paper?
Not yet. I mean, you need to do it at an industrial scale. Uh, uh, it's just a demonstration of a concept. So we have, we showed that, and the predictions are, it has not been done in industrial scale. The predictions are, if it is done at an industrial scale, it could save anywhere from 20 to 40% overall energy. That is from energy to cut down the trees, transportation, all the way to final product, and probably make the products much more eco-friendly. That's the goal, but it's only been demonstrated at the lab scale so far. Yes.
So on the same subject, ignoring the cost issue, are there any specific advantages of pollen over, say, other fibrous plant things, cellulose, whatever? And is there any specific advantage of the sunflower pollen except maybe availability?
The answer is we don't know. So it has not been done comprehensively enough in a number of different systems to draw that conclusion. This itself took about a group of 7, about 5 years to understand how to create these different geometries, digital design, etc. My guess is that based on the limited amount we know so far, there is a broad class of plant species where this could be applicable. And, but there are subtle enough differences between them that we cannot make universal conclusions about one recommendation. But I think that you can make paper with more than sunflower pollen, for example.
So the first part was, if you had fibrous materials, which they can combine, you could create some of that.
It's possible, yeah, it is possible. But we thought that synthetically we can control it much better just by printing on it. And we can print anything we want. We can print an organic coating. We can print something that's removable. And that's why that gives us a lot of flexibility. But I think one way we have looked at your question indirectly is we put constraints. So we put mechanical constraint on plant leaves to study. And constraint is essentially having a directional fiber, that gives you a different kind of constraint. So it is, conceptually it's possible, but we have not done it.
On the diamond part, did you do simulations to make sure that there may not be a reversible phase change, like shape memory kind of effect?
Yeah, so we've done a number of different things. The phase change, if it had been present, we did ultra high. Actually, when we sent the paper to Science, they wanted us, because it's unexpected result, bending diamond this much. So they wanted us to make sure that it was not some artifact of the experiment, first of all. Is it pure enough? It is atomically smooth, nearly atomically smooth enough. And what is is it carbon? Does it fit all the attributes of diamond structure? So we had to do ultra high resolution electron microscopy. So if there was phase change, we would have picked it up. So that's one. The second thing is it's completely reversible, as you saw. And if there was a phase change, we would have picked it up. The third place where we would have picked up, so we did look for the phonon instability, which is a phase change. And it does happen in compression at some point, and we know where it happens. So the conditions under which I showed the predictions to our knowledge so far, are free of phase change. My pleasure.